In this video, we're going to take a look at some applications of right triangles. I'm going to stress throughout this recording that you start with a picture. That is very important. The best way to get information down onto your paper is to graphically set it up. It's really going to show you what you're doing, show you what you're looking for. So always start with a picture. Second thing I will note is that it's very important to make sure that we're dealing with a triangle. We know that it is in fact a right triangle. We may have circles. We've already looked at arc lengths. So if something is traveling on a curved path, we can't use a triangle to solve the length of that path. If something is not completely perpendicular, if we have a triangle that does not have a right angle, we can't use right triangle trig for it. We're going to have to rely on skills later on. So we do want to be aware of what shape we're dealing with. Let's start with example number 1 here. From a point 6 meters from the base of a building, you measure the angle to the top of the building to be 70 degrees. What is the height of the building? So I'm going to draw it out. I have my building, and you don't have to be a great artist because I definitely am not. Now, for this class, you can always assume buildings are built correctly, meaning they form 90 degrees with the ground, unless it's otherwise stated. So for instance, if I said we have the Leaning Tower of Pisa, that's obviously not going to be at a right angle. Or if I say that we have a hill, then again, it won't be a right angle. So if it's not specified that we have a hill or a leaning building, assume it does form a right angle. From a point 6 meters from the base of that building, so I'm going to call this point P right here. And I think it helps to have letters or labels on your points if you are just using points rather than, a more detailed picture. So from a point, we know that's 6 meters from the base of the building. And we know that the angle to the top of the building is 70 degrees. So this angle right in here is called, would be 70 degrees. Now this 70 degrees here, I've written it as the angle from the point to the top of the building. So always be aware of where you're looking from and to. Some of the most common mistakes I see on these word problems are not being able to do the math. It's the English, right? A lot of the mistakes are more English based or just not knowing how a sentence structure is working. So always make sure you're knowing what you're looking from and to. So you measure the angle to the top of the building. We're looking from that point to the top of the building to be 70 degrees. It does make a difference. What is the height of the building? So we're looking for this right here, this side, which I'll label H. One other thing I would point out about this 70 degrees, we'll see this language a little bit more later on, but we can also call this the angle of elevation to the top of the building. Angles of elevation and angles of depression are always based on a horizontal line. Dead horizontal. It doesn't matter what else is happening in the scenario, measured off the horizontal line. So the 70 degrees we can also call an angle of elevation. All right, so we have side H over here that we're looking for. Side 6 is what we're given. We want to compare these three things. We're going to have to use a tangent. We have the opposite, we have the adjacent. So I'm going to set up my tangent. Tangent of my angle, 70 degrees, is equal to h over 6. To solve for h, I'm going to need to multiply that 6 over. And so we're looking for 6 tangent of 70. So pull out your calculators and just type this right in. Now, one thing I will note, it is important to make sure that your calculator is in the correct mode. And so here our angle is in degrees, 70 degrees. So it is important to make sure that you are using your calculator in degree mode. So hit that mode button and then switch it over 2 degrees if it's in radians or RAD. And so when we do this, we should get a height of approximately 16.48. And we need to make sure that we put units on it. Because our initial measurement was in terms of meters, this also must be in terms of meters. All word problems, I do expect you to have them labeled with the correct unit of measure. Let's take a look at number 2. A ship travels at a bearing of north 15 degrees west for 10 miles from the harbor, then turns 90 degrees to a bearing of south 75 degrees west and travels for 7 miles. What is the distance from the harbor to the ship at its most recent position? All right, so let's start with our harbor, because clearly the ship is leaving the harbor. So I'm going to put this point H in here, and we'll measure from there. Ship travels at a bearing of north 15 degrees west. We need to understand how these bearings work. So I think probably most of us are familiar how north, south, east, and west work. If we were to look at a compass, north, south, east, west, or northeast, southwest if we were to go around it. we do need to be familiar with this, and north we tend to list in the top, south in the bottom. However, if you were to look at the map upside down, that would be reversed. As long as we have the relationship between the four correct, it doesn't matter that north's at the top, but that's just a most common position to place it. The ship travels at a bearing of north 15 degrees west. So how we measure this first direction is telling me what I'm measuring off of. So from north, I'm going 15 degrees towards the west. From my harbor here, from my point, which I've called H, I'm going to bend off of this dotted line, which is representing a line north. I'm going to bend by 15 degrees towards the west. And remember, the west was towards the left. So this angle in here is 15. And I know that this length was 10 miles. Another way you might see this written is using words. So we could also write this out 15 degrees west of north. Same bearing, just rather than using kind of the symbol bearings, we've written out in terms of words. So again, we have to understand the English. 15 degrees west of north, so from north, we are bending 15 degrees towards the west. Now, from here, what does the boat do? It turns 90 degrees. So that 90 degrees could go directly out this way, or it could go directly out this way. We're not sure yet. To a bearing of south 75 degrees west. So at this point right here, which is our turning point, I'll call it T, from south, we'd bend 75 degrees to the west. So that tells us we had that indecision of whether it's going to go over here or over here. Went to the left because we can see that 75 degrees is over here. And we know that this length here is 7 miles. We want to know the distance from the harbor to this most recent point, or where we've ended. So I'm looking for this distance here in green, the x. I do know that this is a 90-degree angle. Well, how do I know that? For one, the problem tells me it turns 90 degrees. From going straight, it bent 90 degrees, 90 more degrees to form a straight line. The other way is I know that this angle in here is 15 degrees. So that has to be the same as this angle here. This angle here is 75 degrees because we have some alternating interior angles, and so this is a 90-degree angle right here. Well, sorry, we had that 75 actually directly. I just had that 75 really in an awkward position. Let me move that. 75 was measuring right here. So again, it doesn't change anything. We know that the 15 right here, this is an alternating interior angle. This angle also has to be 15. And then with the 75, that has to be a 90-degree angle. We want to know side x. Well, here we have two of the three sides of a right triangle, and it is a right triangle. That is important to note. So we can use our Pythagorean theorem. 7 squared plus 10 squared is equal to x squared. And 7 squared is 49, 10 squared is 100. So we get 149 is equal to x squared. We're going to take the square root of that. So that would be the exact value, or we can type this into the calculator. And when we type this into the calculator, we should get approximately 12.21 if we round that to 2 decimal places. Now, some people ask me, well, should I be using degrees or radians here? We did not use a trig function. When we need to decide whether we're using degrees or radians is the second we type in sine, cosine, or tangent. The calculator decides, based on the radian or degree mode, how it's going to do the sine, cosine, or tangent. Here we're just putting in two numbers, 7 squared, 10 squared. No angle involved. We don't need to set the mode for anything because it's just two numbers. 12.21, we do want to label that. That needs to be miles, as my two original measurements were. Let's move on to one last problem. The plane's altimeter stops working and the pilot must determine the plane's height. The pilot knows that the plane is traveling at 300 miles per hour and is traveling level with the ground. The pilot measures the angle of the depression to the airport tower to be 10 degrees. 10 minutes later, the pilot measures the angle of depression to be 15 degrees. What is the height of the plane? So we have a lot going on here. Let's start with a picture, just start recording some information. So we have a plane. Its height is unknown. That is what we are looking for. We know that the plane is traveling parallel to the ground, just meaning it's not approaching the ground. It's not actually trying to land. and it's not getting any further away from the ground. So that is useful because we know that that line and the height have to be at 90-degree angles to one another. That's going to be very useful. The pilot measures the angle of depression to the tower. Let me change that line one more time. We'll put the tower over here. That angle of depression there is initially 10 degrees. Remember what I said at the first example, angles of depression, angles of elevation, always based off of a horizontal line. So from the plane's perspective, this is the horizontal line, angle of depression down by 10 degrees. The plane continues to travel, so I'll call this point P1, plane's initial position. 10 minutes later, it's obviously going to have traveled forwards, and we're going to assume a straight line path to the tower here. It's going to travel forwards, and so it's going to be further along that straight line. It's not going up or down, it's traveling level to the ground. It can still spot the tower. Now that angle of depression is 15 degrees. It's gotten a little bit steeper. And so what we have here is actually a triangle that is not a right triangle. We have an angle here, we have an angle actually on the outside. We don't know what the height is, we don't know the hypotenuse, but this shape right in here is not a right triangle. So what I'm going to do is I'm going to form two right triangles. I'm going to look at this triangle here, and I'm going to look at this right triangle right here. Forming two right triangles. Let's think about what we know about these right triangles. If we think about this first blue triangle here, we have no idea what the hypotenuse is. From the plane's initial position to the tower, I don't know what that length is. I don't know what this length is, either the base. I don't know what the height is. The red triangle, don't know the height, don't know this length, don't know the hypotenuse either. I don't have any angles inside, so it seems like I have a lot of unknowns. So let's start working for some knowns. What I do know about this blue triangle is to get from this horizontal line to the hypotenuse was 10 degrees. I can figure out then that this angle in here is 80 degrees. The height and a horizontal line, as we've already discussed, must be at 90 degrees to one another, so this angle in here is going to be 80 degrees. Same logic with the red triangle. This angle here has to be 75 degrees because the height and the horizontal line have to be forming a 90-degree angle. So we have 80 and 75. The heights are going to be consistent. It's not getting any lower, not getting any higher. We don't know what the horizontal distances are, but we do actually know one of them. I know how far it traveled from here to here, or this little segment of the blue line right here. I'll draw that a little differently so it's a little clearer. This distance right here, I can figure that out. We know that the plane was traveling 300 miles an hour. We know that the time it took to travel that distance was 10 minutes. Let's make sure that I've done that correctly. 10 minutes later, there we go, it is. 10 minutes later at 300 miles an hour. So we need to figure out the distance. We're curious what the height is as a distance. So we need a distance. How do we get distance? Well, it is rate times time. We know the rate is 300 miles per hour. The time was 10 minutes. We need the same unit, so hours and minutes. Well, 10 minutes is 1/6 of an hour, 10 out of 60. And so we get that this is 50 miles. We know that this little blue section right here is 50 miles. It does not give me the full length across the base, but it gives me a portion of it. I also know that the red base would be x. So it seems like we have too many unknowns, but I promise you we actually can solve it from here. We're going to see how we can piece this thing together. We're trying to find the height. We have two different triangles that have that height. We're going to need to rely on a side. We don't have any side given, but we're actually given a little bit of this blue side, and so we can set up a system of equations with h and with x to solve these two right triangles. Let's start with blue's triangle. We have an opposite, I pointed the wrong side. If we think about the 80, we have the opposite portion of it. We're looking for the adjacent, so I'm going to be using tangent. Tangent of 80 degrees is equal to this side, this entire side, would be the 50 plus the x. and then the adjacent is the h. The red triangle, the angle is 75, not 25, 75. And then the opposite of 75 would be x. The adjacent is h. So we can set up the ratio x over h. So I have two equations with two unknowns. We can solve this using a system of equations. So we could use substitution or elimination. I do want to find the height, so that means I'm going to create an equation in terms of h. I want h to be in the equation, meaning I'm going to solve these things for the x's. I think that's going to be the easiest way to do it, substitution, solving for the x's. So if I want to solve this top equation for x, I'm going to multiply the h over, and I'm going to subtract 50. And then the red equation, I would just multiply the h over like so. And so now that I have two equations solved for x, I'm going to set them equal to one another. So the top equation, h tangent 80 degrees minus 50 is equal to h tangent 75. And now we have one equation with h in it. I'm going to get the h's to the same side, and I can do that by subtracting either of them. It doesn't really matter. And then I need to get the 50 to the other side, so I've just chosen to make the 50 positive. It doesn't really matter. We would need to factor out the h. So now that I've got h factored out, I can divide by what isn't the h. So I'd have 50 over tangent 80 minus tangent 75. And so we need to plug this into the calculator. Be careful that we use some parentheses around the denominator. So we'd have 50 divided by, and then I'd throw a tangent in here into my calculator. Tangent of 80 minus tangent of 75, and close up the parentheses. So what I've done in my calculator is just added parentheses right here and here. And so when we do that, we should get approximately, again it is an approximate because we are rounding, 25.78, and our units were miles. So this thing quite high, probably a little bit unrealistic, 25 or almost 26 miles above the height of the Earth, so a little bit unrealistic, but we found the height nonetheless. This last problem points out a few really good things to be aware of. One, there's angles of elevation, angles of depression. I cannot stress this enough. Angles of elevation, angles of depression, always measured off a horizontal line. And so that means it's not always in the triangle, as was the case in this example. The angle of depression was outside of that triangle, and so we had to move it into the triangle. So be aware that the angle that is given is not necessarily the angle that we need to use. Draw your picture. I cannot stress that enough. Start with a picture.